work pretty much the same. All right, last time we ended with problem number 20. R cubed equals 343. And let's go back and visit that for just a bit. In other words, do you remember how we solved it?
I'm looking back at my notes now. So number 20.
Yeah. Rather than looking back on your notes, I'd rather know whether you remembered how we did it.
We cubed squared. I don't know the words.
Well, okay, I think we understand what you're saying. We took the cube root of both sides.
There we go.
Okay. Now, we didn't really talk about it, and probably, in fact, the way I wrote it would probably have been that. That's the cube root of that side. That's the cube root of this side. But there's actually a better way to do these. And that is, the cube root means to the 1/3 power, just like square root means to the 1/2 power. Okay? So what I can really do here is exponentiate both sides to the 1/3 power. Same thing as taking the cube root, but it's more powerful. And remember your rules for exponents. What do we do when we are double exponentiating on the left?
We multiply the 3 times 1/3.
So we end up with r. That's our goal. And then the cube root of that number is 7. Okay? Now, if we had the problem was r to the 5th equals 343, then I would need to take the 5th root of both sides. In other words, we're going to use an exponent that when multiplied by this number is equal to 1. So let's take it one step further and say r to the 2/3 equals 16. Now, with the old method, this would be very hard to do because, I mean, how do you get rid of the 2/3? But with our new method, this becomes easier. What do I have to exponentiate that to?
3 2's.
In other words, as long as I exponentiate it to the reciprocal, it's going to turn into r. Now, what is 16 to the 3/2 power? And I'd rather you not use a calculator on this, just because I'm trying to illustrate a point. When you have a fractional exponent like this, the bottom number is the root, the top number is cubed. Always do the bottom first. In other words, what's the square root of 16?
Square root of 16 is 4.
And what's 4 cubed? 64. That's what 4 times 4 times 4 is. 64. Okay? So this method is much better because it now allows us to handle numbers that are not just integers, but fractions. If we have a fractional exponent, all we have to do is raise both sides to the reciprocal of that fractional exponent. All right. Rank these 3 numbers in the order of least to greatest. You can use your calculator on this one if you feel a need. You don't really need to. In fact, it'd be better if you could actually do this without your calculator.
All right, I'll try that then.
Well, the reason I say it is because you don't need exact numbers. All three of these have a different integer number. So all you need is the first digit of all three numbers. So the strategy is going to be to turn each of these numbers into decimals. And then we can rank them very easily. What's pi?
Pi is 3.14.
What's 7/3? Just approximately. Well, divide 3 into 7. What do you get? 3 goes in 2 and change. We'll call it that. I don't care what the change is, because at this point there's no difficulty ranking this number with this number. And then 9/2, what's the first digit?
3.
2 goes into 9 how many times? 4 and change. 2 times 4 is 8. So 2 goes into 9, at least 4, with some left over. But because of this problem, we don't even care what the plus is. Turns out that it's 4.5. Okay, and this is 2.3. But we don't need these. Now rank them. Smallest to highest.
It's the 2, pi, then 4.
So it's the 7/3, then pi, then 9/2.
So that looks like B.
Yeah. And you can see why I didn't need to know what the next digit was. Had this been a number whose first digit was 4, in other words, let's say it was not 4, I meant 2. Let's say that's the problem. Okay? Now, when we go to figure out this one, it's 2 and change. Well, I got to go further. This one, in other words, I can't rank these. Just putting it like that is not sufficient. I got to get at least another digit. Well, 3 goes into 7 2 times. There's 1 left over. 3 goes into 10 3 times. So that's the next digit there. And the next digit there is 5, and now I can rank them. So, particularly for the ACT test, they have a lot of problems like this. Why? Because they don't really want to give somebody with a calculator an edge. They're not interested in people who can use their calculator. So they set up their problems so it's really easy to rank these three numbers in your head without the calculator, which means you can do it quicker. And that's what they want to measure, is speed. Okay. Okay, this is kind of a cool problem. When you are taking the ACT test, and I realize that we're doing these sessions for kind of a dual purpose. We're doing them to refresh you for your class, and we're doing them because you will probably take the ACT test in the fall, if not the fall, certainly the spring. What I'd like you to do is get in the habit of figuring out how you're going to solve it. Which of the three methods are you going to use to solve it? In fact, that should always be your first question. Am I going to solve this thing algebraically? Am I going to solve it by back solving? am I going to solve it by picking numbers and then back solve? Those are pretty much the three methods that you can use to solve these problems. Well, picking numbers usually requires there to be variables in the question and the answer. So we can throw that out. So we got two choices. We can do this algebraically and we can back solve it. And I'd like to go through both of them just to show you the advantages and disadvantages of one over the other. Can you solve it algebraically? Can you give me the equation that I need to write such that we can solve for this mysterious number that I would add to both the numerator and the denominator that would make 9/13 equal to 3/4?
All right. 1/3 to get 9 to 3.
Okay, remember what the question says. We have to find a single number.
Oh, you can add.
Yeah, that we're going to add to both the numerator and the denominator, and it'll turn it into 3/4 instead of 9/13. Those are not the same fractions. Okay, so let's go back and see if we can figure out how to do it algebraically. Because what I'm really trying to convince you of here is that it's frequently very difficult to come up with the algebra on these kind of problems. It's tough to think of it. I'm going to give you a little bit more time before we go to the back solving, or before I tell you how to do it. But it's difficult, and yet back solving always works. Let's do back solving. And then when we get done doing back solving, I'll show you how to do it algebraically.
Okay.
So,
all right.
Work me through how this is going to work by back solving.
We'll start with the problem, the answers that they gave us.
Okay, we'll just go from front to back. That's fine. That's not typically the way you want to do it, but this is a little bit of a different kind of problem, and I'll explain that. But let's try this. So does -3, can that be the answer?
No, it cannot, because 13 minus 3 only equals 10.
Well, that could be correct, but 9 minus 3, so if -3 were the answer, I would have to subtract 3 from top and bottom. And that is 6/10, which is not 3/4. Okay? Now, we're going to try all of them, but let's get into the habit of trying the easiest ones first. With a problem like this, where we may have to try all 5 of them. You know, but if your life depended on it, that's what you would do. You would try all 5 of them. So the next one, let's not try that, because the math is going to be hard on that. Math's going to be hard on that. Those may be the correct answers, and we'll get to them. But first, we're going to try these 2 easy ones. Does J work?
9 plus 3.
12.
And 13 plus 4.
No, it's got to be 13 plus the same number. In other words, you have to add this number to both the numerator and the denominator. It's not adding these 2 numbers over here. It's adding a single number to both. So if we added 3 to the numerator, we need to add 3 to the denominator. And now the only question is that 3/4? Well, I tell you what, you got your calculator in front of you?
Yes.
What decimal is 3/4?
It is 75%.
What decimal is 12/16?
75%. We have our answer.
Have our answer. Okay. Worst case scenario was we would have had to go through all of these. Now notice that the math on that one would have been a little dicey. It would have taken a long time. If I subtract 1 1/4 from the numerator, I have 7 3/4. And if I subtract 1 1/4 from the denominator, I have 11 3/4. Now I got to figure out what the heck that is. Is that 3/4? You know, if I have a calculator, it's a little easier, but it's more of a difficult back solve. So that's why I say always try the easiest numbers first. Although there are certain back solving problems where you're going to know whether your guess is too big a number or too small of a number immediately. There are the problems that I call age problems or marble problems. An age problem might be Andy was 3 times older than Jim, and Jim is 6 years older than Mary. In 3 years, Andy will be 15. What are each of their ages? Well, those are classic problems that you should back solve, because when you try a number and if it isn't correct, you're going to know whether you have to go bigger or smaller, always. Or a marble problem, same thing. This, not so much. If we tried this number right here and it wasn't correct, I'm not positive we would know whether we needed a bigger number or a smaller number. It wouldn't be as obvious. So with this problem here, the way to back solve it is to go with the easy ones. Try F, try J, try K. If none of those work, then go to these two. But with a lot of problems, you're going to want to start with either the second low number or the second high number.
I understand. That makes a lot of sense.
Yeah, because if you knew which, in other words, let's say we start with 3, and it's the kind of problem where 3 isn't correct, but I know I need a bigger number, I'm done. I know 6 is the answer. So there's huge advantages if you're going to know which direction it's going to go. Oh, I told you I'd show you the algebraic way. Okay, the algebraic way is 9 plus some number, which we're going to call x, divided by 13 plus that same number, has to equal 3/4. Now you have that equation to solve. And you can solve it by cross-multiplying. So we get 36 plus 4x equals 39 plus 3x. Solving for x, move the 3x over this way, move the 36 to that side, and you get x equals 3. So relatively simple to solve, but not that simple to formulate. And that's the same case with an awful lot of these problems. It's not the algebra that's tough to do, it's the formulation of the equation that is difficult to do. Which means that back solving is usually the best way to solve those kind of problems. We've got time for one more. What's the slope between these 2 points? And this is something that's probably the most basic thing in algebra that you're going to need to know.
They gave me a graph in geometry when I did this, so I know how to do it on a graph.
What's slope defined as?
The
rise over run. That's all you ever have to remember. Those 3 words. Slope equals rise over run. Now, we're talking about the slope of a straight line, okay? So if I have a straight line like that, well, the rise is the difference in the y-coordinates. Let's say we want the slope between this point and this point. the rise is always the change in the y's, and the run is always the change in the x's. Or I can write that in the more conventional but harder to remember form, y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Now, do you get all of that? In other words, this is x sub 1, this is x sub 2, this is y sub 1, this is y sub 2. So
Yes.
the distance between there and there is the rise, that distance right there, and the run is this distance between there and there. And the reason slope is part of algebra 1, 2, and 3 is because the concept of slope is the key ingredient in differential calculus. If you had to say 3 words to define differential calculus, it would be rate of change, the instantaneous rate of change. And rate of change is slope. Notice that the rate of change means the change in y divided by the change in x. So the rate of change, and as long as you have a straight line, any 2 points give me a slope. The slope between these 2 points is going to be the same thing as the slope between those 2 points, even though I didn't quite draw this straight. I meant to. So any 2 points define the slope of a straight line. Okay, well, let's figure out what it is between these 2 points.
All right.
What's y sub 2?
7, negative 7.
Negative 7. Subtract, what's y sub 1?
4.
What's x sub 2?
2
And x sub 1?
minus 5.
And now simplify that expression for me. What's minus 7 minus 4? This you need to be able to do without a calculator.
Negative 11. I did it without a calculator.
Okay, good.
And the bottom one's negative 3.
So keep simplifying. Just positive 11/3. In other words, you can't reduce it anymore, but you can change it to a positive 11/3, which is going to be our answers. You're not going to see a minus 11 divided by a minus 3 there, because we're always going to turn that into a positive 11/3. Now, something worth noting here is that you can also reverse these if you want. If it makes the math a little easier, as long as you reverse both, it won't matter. I can do y sub 1 minus y sub 2 as long as I do x sub 1 minus x sub 2. And sometimes it really does make the math a lot easier. It's 4 minus a minus 7 divided by 5 minus 2. Well, the top is positive 11. The bottom is 3. It actually saves 1 step. We don't have to do this last conversion. But if you're going to reverse them, make sure you reverse both. If you reverse the top without reversing the bottom, you'll get the number on the slope correct, but you'll get the sign wrong. Okay?
Okay.
All right. Let's see. We started at 5:45 or 5:40? Remember? How long do you want to go to? I can go to either one. 6:10 or 6:15? Right now it's 6:04.
6:10 is good.
Okay. All right, prime numbers. Again, probably not, well, you might get prime numbers. You will in your algebra class, but the ACT test is particularly heavy on not just prime numbers, but number theory. Okay, let's talk about number theory for just a moment. Because number theory is something that you probably didn't get much of in algebra, geometry, you won't get much in algebra 2. You might have gotten some number theory back in 4th and 5th grade. But when I talk about number theory, I'm talking about things like an even number times an even number is an even number. An even number times an odd number is what?
A negative number. I mean,
no.
An odd.
It's actually still even. In other words, the way you can always figure these out is just pick numbers. Even times even is even, and even times odd is actually even. 4 times 3 is 12. Always. No matter what odd number you pick, if you multiply it by an even number, you get an even number. The only thing that's ever odd is an odd times an odd. So only 1 out of the 3 possibilities results in odd. Most of the time when you multiply 2 integers, you're going to get an even, 2/3 of the time. Okay, more number theory. Well, this isn't really number theory. I think what you thought I was talking about was negative times negative.
Yeah, that's what I was thinking about.
That's positive. Negative times positive is negative. Those kind of things. That's also number theory, but that's stuff that I would expect you automatically to know.
Yes.
Whereas the other number theory is involving prime numbers. Count off prime numbers for me, starting with 2. 2 is prime.
All right, 7.
3. Remember the definition of prime. It can only be divided by 1 and itself.
5. 7.
Of course, we don't need to consider even numbers anymore, because all even numbers greater than 2 can be divided by 2. So just test only odds.
11.
From here on up.
13. 17. 19.
It's pretty good. That's far enough. You know how to do it.
Yes.
Okay. So let's talk about problem 24. Do you know how to find the greatest prime factor of a number?
It's a factor of a number that's prime, but it's the largest prime that they're
counting. The largest one. But what I mean is, if I told you break that down into its prime factors, what would the first step be? It's usually referred to as a tree. In other words, the first thing I'm going to do is cut it in half. Right?
Yeah, and there you go.
That's there you go. I can't cut this down any further. That's prime. That's prime. So there's the largest prime factor of 38. Now let's do the same thing with 100. What are the first 2 things?
50 and 2.
Well, 2 is prime, so I can't go any further with this, but 50 isn't.
Uh, 25 and 2.
And 25 I can still break down.
5 and 5. So 5 is the greatest prime factor.
So 5 plus 19 is 24. And that's our answer. So some of these problems look hard, but they're actually pretty easy. And
Yeah.
that's not unusual for the ACT. You got to be careful. I know that the best way to take this test is to go through it once, and if a problem looks too difficult, put a check mark by it and come back to it after you've seen all the problems. Because the worst possible mistake you can make is never seeing problem number 60. Because problem number 60 might be very easy. It might take you 10 seconds to do. So you always want to make sure you get a look at all 60 problems. And the first time you go through it, you're going to have 60 minutes for 60 problems. You need to keep track of your pace. You want to approximately be taking a minute per problem, but you want to be a little ahead of your pace the first time through. Because in order to look at 60 problems, to guarantee that you look at all 60 of them, you're going to have to do that in like 50 minutes. Because those final 10 minutes, you're going to need that to go back and, if not answer the more difficult ones, guess at least on them. Actually, the biggest mistake you can make is not answering a question. Okay, you always want to guess on both the ACT and the SAT. Now, it used to be that the SAT, they penalized you for guessing, but they're changing that starting in 2016. So when you take...
Why did they penalize for guessing?
Oh, they would take off a quarter, and it wouldn't really matter because you're still better off guessing. Your expected value from a probabilistic point of view was still the same. So I'm not sure what they thought they were accomplishing, but for sure, don't leave anything unanswered because you can see that you're going to have a 20% chance of getting it right by guessing. There's only 5 answers. So by not answering it, you get it wrong for sure. By guessing on 5 questions, one of them you'll guess right in general. So by all means, don't leave any questions unanswered. And in order to do that, you kind of have to take this strategy where you try to look at all 60 problems with some time remaining. You don't want to get to problem 60 with 30 seconds remaining, because then you don't actually have time to go back and guess on the ones that you put a check mark saying, I'm going to look at these later. All right, Emily.
All right. Well, thank you very much.
You're welcome, and I will talk to you, I think tomorrow?
Actually...
Yeah, no. I was getting you
the 14th.
Somebody else. Yeah, whenever your next appointment is.
Yeah.
Talk to you then. Okay.
All right.
Bye-bye.
Talk to you soon.